Hello, welcome back to Dinosaurs. We're going to continue through Module 5 here today. So last time we bid adieu to our dinosaur friends. Today we're going to talk about kind of all the things that happen after the dinosaurs are out of the picture, or I should say all of the non-avian dinosaurs are out of the picture. And then we're going to talk about some fossil sites on the different continents. Then we're going to explore some representations of dinosaur in pop culture. And then we're done. We're getting to the end here. But before we get into today's lecture, some announcements as always. If you have questions, somebody else probably does too. All right, so let's move along. Let's review what we talked about last time. So last time we talked about the dinosaur extinction. So what was the cause of the end Cretaceous mass extinction? So take a look at the options there. Take a look at the available options. Just some funny comic memes there. All right. So it was probably an all of the above kind of thing. The asteroid impact gets the publicity, the asteroid impact gets the buzz. Volcanism and climate change were already probably making things difficult, but certainly the asteroid was the final nail in the coffin. And we talked about all those different issues with the fossil record about having problems definitely identifying definitively what was the cause. In these events like these major mass extinctions, there probably isn't one cause. It's probably an all of the above kind of thing. The only thing that wasn't significant was, this was originally proposed, is that the mammals ate all of the dinosaur eggs. So as the mammals became more prominent, they started eating dinosaur eggs, and dinosaurs couldn't defend against that. That's not what happened. It certainly did happen occasionally, though. So mammals did certainly eat dinosaur eggs, and in some cases even ate dinosaur young. So mammals weren't always quite as timid as we often portray them, but they didn't cause the extinction. It was these larger scale impacts. What are some traits that help an organism to survive a mass extinction? So we've seen this before with the other mass extinctions where certain organisms don't make it through and certain organisms do. And after the mass extinction, we see a diversification from the survivors that make it through. So what are some of these traits that might have made it more favorable? Why did dinosaurs go extinct? Why did the non-avian dinosaurs go extinct and the birds did not? All right, so another kind of trick question. Being a smaller body size helps a lot. Smaller body size doesn't need as much resources. Having a versatile diet helps a lot. If you're a very large, very specialized carnivore and all of the very large herbivorous animals go extinct, you're going to have a problem. Being an omnivore or being able to take advantage of any situation that comes your way, that's very advantageous. And then also being able to burrow or even hibernate is also advantageous. So Lystrosaurs made it through the Great Dying because they were able to burrow. Thrinaxodon, same kind of thing. Smaller animals are much more likely to be able to do these things. And so they're much more likely to make it out on the other side. And so the larger, more specialized carnivorous, non-avian dinosaurs all go extinct, but the birds don't. The birds make it into the modern world. It's not physical fitness. So remember, survival of the fittest doesn't mean necessarily biggest, strongest, fastest. It means the ones that are the best fit for the puzzle at the time. At the end of the Cretaceous, after that meteor impact, during that subsequent impact winter, being biggest, strongest, fastest was no longer an advantage. It became a disadvantage and something that we might not consider as fit. Again, the meek shall inherit the earth in this case. We definitely wouldn't consider those little rodent-like early mammals more fit than the dinosaurs, but they were a better fit to that environment. Okay, so let's move into the Cenozoic, the period in, or the era in which we live now. So Cenozoic means new life or modern life. The first part of the Cenozoic is the Paleogene, I'm not going to ask you to remember any of these geologic time period names. This is a dinosaurs class. We're primarily interested in the Mesozoic. We need to know Triassic, Jurassic, and Cretaceous. We do not need to know Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, Holocene. We don't need to remember those. So you'll see them on the slides. I'll mention them just so you can keep up. Paleogene is the first part, representing all the way up to the Pleistocene here. What's it look like? So this is from the Miocene 50 million years ago. So this is about 16 million years after the dinosaur extinction. And what you'll notice is that we recognize a lot of these features. Earlier on in the Mesozoic, it was very difficult to kind of pick out which continent was which. Things look very different. This is pretty easy. Some things you'll notice though, Central America, not really very well developed yet. Australia just rifted off from Antarctica. India hasn't yet collided with Asia, and the Mediterranean is much wider and much larger. Africa continues to kind of push north in there. Another thing you'll notice is that if you look at the continents, there's a lot more green. And if we look at the temperatures, the early parts of the Cenozoic, we often associate the time after the dinosaurs with the ice ages, but the ice ages are a relatively recent thing. So the early part is actually very hot, 15 degrees warmer than today, very similar to the conditions kind of at the end of the Permian when the warming led to a mass extinction. In this case, though, the continents are kind of widely separated. There's not very many places that are really far away from water. So the end of the Permian, start of the Triassic was very arid and dry. This is not. So it's hot and it's humid. There's evidence of kind of rainforests, tropical rainforests, all the way onto Antarctica. So Antarctica is green. The Earth is probably completely ice-free, and there's a very small gradient, a very small temperature change from north to south. The entire planet is full of lush, vibrant forests. It's very unlike the Permian hothouse, even though the temperatures are pretty similar, because again of the continental configuration. So that's the sort of impact that plate tectonics and just the sheer coincidence of the position of the continents can really dramatically affect it. The Cenozoic, though, is defined from this early hothouse, and then from the Eocene forward, we see this slow descent into cooler and cooler and drier conditions until we finally get to the Pleistocene, where we really fall off of this. This defines the start of the Pleistocene, the start of the modern geologic era, the Quaternary, and we kind of bounce back and forth between glacier into glacier, and then there's this small period of relative stability in which all modern human civilization, agriculture developed. And then getting out into the future, it's labeled here as the Anthropocene, the future, it's still to come. We're on an upward trend. This cooling trend has reversed. It had naturally reversed already. The glaciers were already receding, but we should actually probably be entering into another cooling phase. We should be entering into another glacial period, but we're not. How hot is it going to get is somewhat up to us. You see here it's labeled RCP 8.5. That's a representative concentration pathway. So this is one possible scenario for our global CO2 concentrations. This assumes no action on emissions whatsoever, just business as usual. The increase in emissions that we're seeing just continues unchecked. And we would end up eventually returning to this sort of Eocene hothouse climate. There are many creatures on Earth that thrived in these conditions. Forests in Antarctica is not necessarily a bad thing. So there's nothing inherently wrong with returning to these warmer conditions. The problem is that we're returning to these warmer conditions very abruptly and very quickly. And life, even us as living organisms, will find it very difficult to adapt to these changes at the pace that they occur. And so that's really the problem. It's not a problem that the globe is getting warmer necessarily. It's not even probably trending towards the warmest that it's ever been, but the rate is problematic. And if we check our emissions, some of these other scenarios are possible, although this lowest scenario, the 2.5 scenario, is probably already not possible given our, really frankly, our relative inaction on climate change. So what else is happening in here? You see a little arrow here to the Rocky Mountains. We've been talking a lot about the development of the east coast of the United States during the assembly of Pangea, the Allegheny and orogeny, Africa and Europe smashing into North America, raising the Appalachian Mountains on the east coast. We didn't really talk about the west coast. The west coast here, the Rocky Mountains. The Rocky Mountains are bigger and taller and pointier than the Appalachians because they're newer mountains. They only arise during this tertiary, the Paleogene period. And the reason that they evolved was there was subduction of the Pacific plate along the west coast, which usually we would expect volcanism along the coastline in this scenario, like we see in the Andes of South America. And we do see that in northern North America, like the Cascade Range, and we see it in Central America and Mexico, but in the central part here, we don't. The reason for that is that the slab here is very shallow, and so it doesn't reach down far enough into the mantle to actually start melting. And so instead of getting volcanoes, we actually get mountains and folds and compression very far inland, kind of oddly far inland from the margin. And so that's how the Rocky Mountains are created, by this sort of very shallow angle subduction. Another thing that happens is this compression resulting from this actually uplifts the Colorado Plateau. If you've ever been to the Grand Canyon, one thing that's pretty striking is that it's this massive, massive canyon. It's quite grand in scale. And at the bottom is a relatively small river, the Colorado. How did this relatively small river carve this massive canyon? Well, it sort of had help. Rivers can only curve down to their base level. And what's happened is that it wasn't so much the river carving downwards as it was the plateau moving upwards and the river sort of moving down through it as the plateau raised up. So without this uplift, without this compression, without the creation of the Rocky Mountains and the Colorado Plateau, we wouldn't have the Grand Canyon. The river would not be capable of doing this. So another feature that we see is that it created Monument Valley. So if you're a fan of the old John Ford Westerns, this feature is prominently in there. You see differential erosion taking place. This big chunky sandstone at the top is much more resistant. It resists erosion much more than the lower shales here. And so it remains as this erosional remnant. And you get these kind of weirdly spectacular landscape features from this differential erosion. The hard resistant rocks remain and the soft rocks are gone. And we get these really neat formations. So that's the kind of the North American tectonic story. On the other side of the world, India has now finally docked with Asia. India had broken off from Africa in the Mesozoic, and it traveled across the entire width of the Indian Ocean. And about 10 million years ago or so, it actually started colliding. So the Rockies are taller than the Appalachians because they're newer. The Himalayas are brand new. They've only been really forming for about 10 million years, and they're actually still actively being uplifted today. So that's why they're the tallest mountains on Earth. At one point, the Appalachians were probably Himalayan scale, but they've been eroding away for 250 million years. The Himalayas are brand new, fresh baby mountains. If we go into little Europe in the West, the Alps are being formed in a pretty similar process as Africa moves north, closing the Mediterranean. Eventually, it's going to completely collide with Europe, and the Alps will be Himalayan scale. So there'd be kind of this continuous, massive mountain range all the way from Europe through the Middle East and all the way down through Southern Asia. But it took about 100 million years for this to happen. And again, the mountain building continues today. This is Mount Everest. At one point, there was only a handful of people that had actually gone up the summit. It's so high up there, there's so little atmosphere above you that generally people need supplemental oxygen. So like they need oxygen bottles to hike up there. And there's been so many people, so much increase in tourism that there's actually been lines forming at the summit. And fairly recently, people actually died because they ran out of oxygen waiting to get up there. It's been a big problem, this massive influx of tourists into this area that's really not equipped for it. It's a very dangerous proposition to hike up Mount Everest. One of the checkpoints along the way is called Green Boots. It's actually literally a person that died on the way to the summit that was wearing green boots, and they're locked in the ice and they haven't been moved, and so they're actually used as a reference point on the way up. So a pretty eerie reminder of just how dangerous this place is, and really kind of a telling sign of modern life, and that even in these reaches, human impacts are obvious. Another thing happening tectonically is that Africa starts rifting apart. About 25 million years ago, the Somali plate, Somalia starts actually breaking away from the rest of Africa. The Nubian plate, the Red Sea and the Gulf of Aden open up as a result of this, separating the Arabian plate from the African plate. Eventually, this rift is going to progress through, and it'll be this little tiny ocean. The Red Sea will actually connect all the way up through. But currently, under the current situation, it hasn't quite broken through yet. Africa is still actively pulling apart, and it creates these very deep, very linear valleys. Some of the largest lakes on Earth are here: Lake Malawi, Lake Tanganyika, Lake Victoria. They're all in these rift valleys here. And one of these very large valleys is known as Olduvai Gorge in Tanzania, and it actually records a lot of very early hominin activity. These are the Laetoli footprints, which is a trackway. Remember, we talked about trace fossils earlier and how valuable trace fossils are in giving us insights into dinosaur behavior. These early trackways give us insight into early human behavior. And we can actually see that there's more than one individual here with more than one size. So very telling, very cool story here. Modern humans walking on the now lithified surface. But this is evidence of an early hominin walking across this surface when it was still muddy. You see there's other animal tracks here as well, but very neat example of trace fossils providing insights into our early evolution. It's also a good example of the impact of plate tectonics, the lithosphere, on the development of evolution and the biosphere. Remember, these things are all linked together. It's all a linked system. Changes in one system impact changes in the other, and I hope that's something that you're getting from this course. You see how plate tectonics influence the atmosphere, how the atmosphere influences life, how life actually provided the atmosphere. So all these different interlinked relationships. And probably the coolest feature, or maybe the scariest feature of modern tectonics is the Yellowstone hotspot. So Yellowstone Park out in Western North America, this is the current position of Yellowstone. Yellowstone overlies an active mantle hotspot. So if we think about like Hawaii, if we think about Iceland, if we think about Easter Island, some of these island chains that are in the middle of the big oceanic plates, the reason those island chains are there is because there's an active mantle plume where a lot of material, a lot of magma is rising to the surface, and active volcanism in the form of volcanic islands. Yellowstone is an example of this happening on the land. So this is a continental hotspot. And so this North American plate has moved over this hotspot through time. The mantle plumes remain relatively fixed, and the plate kind of moves over it with time. And what you can see is that the Yellowstone hotspots actually scorched a path through the mountains here, and you can actually see where it was in the past. There's also this series of increasingly younger calderas towards the modern crater. So there's eruptions dated to 2 million years ago, 1.3 million years ago, 600,000 years ago was the most recent. When is it going to blow next? Well, let's see what's the recurrence rate here. 700,000 years, 700,000 years. It's been 600,000 years. So nature is not under any obligation to act on cycles and arrive on time, but sometime within the next 100,000 years, hopefully not anytime soon though, we would expect a eruption here of the Yellowstone supervolcano. So what would that look like? Well, if we look at historical volcanic eruptions, such as Tambora in 1815, the eruption of Mount Tambora in 1815 resulted in the year without a summer. All that ash, all that soot in the atmosphere, we talked about this last time. We were talking about the impact winter. Remember, this was the summer where the French Revolution really kicked into gear due to food shortages. Mary Shelley and wrote Frankenstein and the Origin of the Vampire Myth. That was from a relatively small volcano eruption with respect to the scale of what a Yellowstone eruption would look like. Even the small Pinatubo eruption in 1991, and I say small relative to Yellowstone supervolcano, that caused temperatures to drop by about 1 degree C for a year and impacted our weather, our climate. Yellowstone would have a much more dramatic impact. It would likely drop global temperature for decades as opposed to a year or two. We've also seen in the relatively recent past, Eyjafjallajökull, a little volcano in Iceland, erupted in 2010. You probably remember this. It kind of grounded air traffic in Europe for about a week. I was actually working in Norway at the time, and I got stuck in Norway for another week. I wasn't going to have any time to walk up in the fjords, but all of a sudden I did, so it worked out pretty good for me. But this is a relatively small, relatively narrow plume. You see, compared to Pinatubo, which had a much larger plume, the plume from Yellowstone would be orders of magnitude larger and more significant than even this. And even this relatively small plume had fairly dramatic impacts on Europe and surrounding areas. If Yellowstone erupted, this is a simulation of the ash thickness over the continental United States. We'd be relatively okay here, a couple millimeters of ash, certainly not ideal. We've seen, again, like the wildfires out west, how even that small amount of soot and ash in the atmosphere can affect our sunsets and kind of put a haze into our air. This would be ash actively raining down from the sky. Not so big a problem here, but you see over the central United States, it would be much thicker. Think about how annoying it is to shovel snow. You shovel your driveway, you shovel snow into a pile, that pile eventually melts. If ash falls from the sky, you shovel ash. Ash is about 3 times as dense as snow, maybe more so, depending on the moisture content. You shovel ash, it's way heavier. That pile's not going to go anywhere. It's not going to melt. It's also going to choke out all the crops in the central portions of North America. The breadbasket of North America would be under a thick blanket of ash, in addition to all the struggles that photosynthesis would already have from the ash clouds in the air. This would be a very catastrophic thing for North America and really the world once the global temperature drop kind of kicks in. So hopefully it's not going to happen anytime soon. The magma chamber underneath Yellowstone, though, that's what powers all those geysers and hot pools and mud boils and things like that. But remember, the modern Yellowstone Park is this active volcanic caldera, and we can actually track the motions of the magma plume under the ground by sending sound waves into the earth. We can also see the topography subtly changing as the magma moves around. Hopefully we'd be able to see an eruption coming, but frankly, there's not really a lot that we could do about it other than just get ready and hope that the worst doesn't happen. But hopefully this is a long way off, but it's a very scary proposition. So moving into the Quaternary is the last 2.6 million years. So in geologic time, that's a flash. Quaternary paleogeography is modern paleogeography. If we look at this reconstruction, that's the modern world. There are some subtle differences though. One thing you'll notice is this big white blob here. That's the Laurentian ice sheet, the big ice sheet that covered most of New York State. There's also an extensive Antarctic ice sheet and then some southern ice sheets here on South America as well. All of that ice is water that was in the oceans that's now locked up on land. So sea levels are also a little bit lower than they are now. And you can see that, Australia is connected to Papua New Guinea and some of these other islands. The Indonesian islands is actually kind of a platform of dry land. You see a lot of dry, arid areas here. You also see the land bridge. North America and Asia are connected by a land bridge. Right now, there's a relatively narrow strait of oceanic water between them. At this time, that's not there, and they're connected. And many animals, like these, use that land bridge to move across between the continents. And one animal in particular, us, also did that. So humans originated in Africa, walked out through the Middle East into Asia, and eventually crossed over into North America and down into South America to start populating the world. Indonesia and Australia came a little bit later, but that's our story. And again, we see how changes in geography impact changes in biology. We talk about these ice sheets, and again, I'll show you on the next slide how thick these things were, but the ice actually moves. So why does the ice move? Why did these glaciers actually flow? Glacial ice, when we think of ice, we think of it being solid. So if you go into your freezer and you grab some ice cubes out, it's pretty hard. If you've ever fallen onto a patch of ice or went ice skating and took a dump, you know that ice is very hard, but it's not really solid. Over long time frames, ice actually flows. It flows under its own weight. So what we have in this during the Ice Age is lots of snow accumulating and building up in the higher northern latitudes, and it piles up and up and up and up. And under its own weight, it sort of collapses. So think about like pouring a bucket of slime out onto a table. Initially, the slime is going to be piled up into a heap, but the weight of the slime is going to cause it to collapse and move outward. That's what ice does. This is the Elephant Foot Glacier in Greenland, and you can see it very much resembles the slime kind of oozing out there. The glacier is flowing under its own weight. And as the ice flows, it's pulling rocks and sediments along for the ride. And so we see all these different features that the ice carves and sculpts as it goes. So, for example, all the rocks that are entrained in the ice, as they move along, they can scuff up and scratch the bedrock. And so we can actually reconstruct the direction that ice was flowing from these scratches and scours in the bedrock. Particularly around here, there's also these drumlin features, which are sort of these spoon-shaped ridges that are very steep on the northern side towards where the ice was coming from, and sort of narrow and less steep on the down ice side. You'll notice they're mostly oriented kind of north-south. These also track the direction that ice was flowing. How far did the ice get? Well, think about like a snowplow clearing a parking lot. There's the big pile of snow and plastic bags and McDonald's bags and discarded hats and gloves ahead of the snowplow in the parking lot. When all that snow melts, all that stuff is left behind. As the glacier is moving, it uproots trees, digs up rocks, scours dirt, and then it pushes it into a pile. And then when the glacier retreats, that pile is left there. It's called a moraine. Along the southern parts of New York here, there's something called the Valley's Heads Moraine that actually kind of dams up the Finger Lakes on the south side. It's this big pile of unsorted rocks that the glacier is just kind of dumped there. And you can still go walk on it today. It's still there. It marks a point where the glacier is stopped. There's another moraine that's a little bit farther south that actually contributed to the formation of Long Island, and a little bit farther out here, Cape Cod. This again marks a position where the ice stopped. So we can reconstruct the ice. It's been melted for 12,000 years, but there's still effects on the modern world that we can still track and see. How thick was the ice 21,000 years ago at the height here in Montreal? 3,300 meters, 3 kilometers of ice. Toronto, 2,100 meters of ice, 2 kilometers of ice. Boston, a little over a kilometer. We here in Oswego, we're probably somewhere in between here. It was about a mile thick of ice. The city skylines that you see here, here's the CN Tower. It's like 6 CN towers tall worth of ice. We always talk about the negative consequences of global warming. This would be the negative consequences of global cooling. So in many ways, global warming is beneficial because we avoid this next ice age. But again, it's not so much the cooling or the warming, it's the rate at which it's happening. The warming's happening so fast that animals, and particularly probably us, are going to struggle to adapt. That big ice sheet had radical consequences to our topography. Right here in Oswego, right out the back of the lakeside dorms is Lake Ontario, a great lake. It's a lot of water out there. How did that big hole that the lake occupies get there, and where did all that water come from? Well, if we look into the subsurface, Lake Ontario occupies a low spot where less resistive rocks of the Queenston Shale were eroded away, and more resistant rocks on the north side. It's the limestones of the Trenton and Black River groups in Canada. On our side, if you go out to the lakeshore, it's the resistant Oswego sandstone, that gray sandstone that you find outside the backs of the lakeside dorms. That's Oswego sandstone. It's a very resistant quartz sandstone. The less resistant rocks in between those two groups has been kind of scooped out by the glaciers. It was probably, before the glacial periods, a river system with these tributaries coming through and flowing out what would have been the Paleo St. Lawrence River. But these river valleys were widened by the glaciers and scooped out into some of the largest lakes on Earth today. The Finger Lakes formed in a fairly similar way, where the Finger Lakes probably existed as a northern draining river network, a network of river valleys. And as the ice moved through those valleys, it sculpted and eroded away at the edges. This is, I think, Cayuga Lake. You see that kind of classic U-shaped valley here. The ice scooped out the valley, left some of the tributary valleys, like say Watkins Glen, high and dry. That's why there's that big, massive canyon carved through the sides. Those used to be feeding into this river system, and they were left as hanging valleys. And again, you see the valley's head moraine here, this big pile of glacial debris that marks where the ice stopped for an extended period of time here. But the reason the Finger Lakes are so long and skinny and narrow and northerly oriented is because the glacier came through and carved out these valleys that already existed there. As the ice retreated, it also carved the landscape out here. One obvious consequence is that at the time, the Lake Ontario basin was much larger, and we actually named these glacial lakes a little bit differently. So we had here Glacial Lake Iroquois is kind of Paleo Lake Ontario. It was Lake Ontario before Lake Ontario was Lake Ontario. And you see that it's much larger than Lake Ontario. It extends all the way to the Niagara Escarpment, the Onondaga Limestone, kind of the modern path of the Erie Canal. Everything north of that was underwater. The lake plain was underwater. Some of the onion fields around here, that very rich organic black soil, the muck that the onions grow in around here, that's sediments from these proglacial lakes. You see the Tug Hill Plateau was high and dry. The Adirondacks were high and dry. But a lot of the areas, coastal areas, were flooded with this lake. You can actually still see the paleo shoreline. You can find this long strip of gravel, very similar to the lakeshore near Rudy's. We see that inland a little bit farther and up elevation from this remnant glacial Lake Iroquois shoreline. If you go out west, 104 is called Ridge Road. It actually runs along this ridge of gravel that was the old shoreline of this expanded glacial lake. All this water came from the melted glacier. You'll notice that the St. Lawrence here is covered by ice, and so all the water from the new Great Lakes, the expanded glacial versions of these Great Lakes, couldn't make it out the St. Lawrence. And so initially, all the water flowed out the Mohawk River. If you're ever driving on the thruway and you're in the kind of the Utica area, coming from the west, you start descending down into the Mohawk Valley, and you see this massive valley open up in front of you, kind of separating the Allegheny Plateau from the Adirondack Dome. And at the bottom of this massive valley, you see this relatively small Mohawk River. How did the Mohawk River carve this massive valley? Well, the answer is that the modern Mohawk River definitely didn't. All of the drainage of the Great Lakes was going out the Mohawk. And so at that time, the Mohawk was much more similar to the St. Lawrence. And there's actually evidence of this in the Little Falls area, where these massive potholes that are carved into the ice, where there was these plunge pools, waterfalls, massive amounts of water that were moving through there, were only left behind now in the form of the valley. As the glacier retreated a little bit farther, the St. Lawrence is still not open, but the flow started going down the Champlain Valley and out the Hudson. And again, in the modern day, the Champlain Valley, the Hudson Valley, it's a lot wider than it should be. The glacial outflow widened these valleys. All of the outflow from the Paleo Great Lakes was going down this valley and carving this out. You see these Glacial Lake Albany, Glacial Lake Corville, I guess it's called, remnants of all this water flow out. All of these widened valleys are relatively new phenomenon. Eventually the ice retreats enough and the St. Lawrence opens, and we see the modern configuration with the Great Lakes flowing out the St. Lawrence River Valley. So that's kind of what's going on tectonically, what's going on climatically, what's going on geologically, what's going on biologically. The Cenozoic is defined as the age of mammals. So that end Cretaceous mass extinction did away with the dinosaurs, the non-avian dinosaurs anyways. And so the large herbivorous dinosaurs are all unfortunately dead. The hadrosaurs, the sauropods, they're gone. The large carnivorous dinosaurs are gone as well. So T-Rex and their like, they're all gone. That leaves those roles open, and what expands into those roles in the cooling and drying environments of the Cenozoic, mammals are particularly fit for that. Their warm-blooded fur coverings is very suited for this cooling climate. Maybe they didn't do quite as well in the very beginning because of that hot climate initially, but you see kind of all the way back in the Mesozoic before the mass extinction, the monotremes kind of break off. But really the diversity of mammals is pretty limited until we cross over the mass extinction and into the Cenozoic. And then there's this explosion of diversity. in mammals. Mammals rapidly diversify, and they rapidly take all of those help wanted signs down and fill those niches that are left open when the dinosaurs died. Marine invertebrates also recover, corals take over, and we see the flowering land plants, the angiosperms really dominating the land. We also see that dinosaurs aren't necessarily really gone. Remember that birds are technically dinosaurs. Birds are avian dinosaurs. The avian dinosaurs survived through the mass extinction. And when we get to the Cenozoic, they diversify to fill those roles. So pterosaurs are gone. Pterosaurs are extinct. Mammals evolved to fill that large flying niche, although not as large. Owls, hawks, ducks, penguins, vultures, a lot of the modern types of birds, they appear first in the Paleogene, the early portions of the Cenozoic. And songbirds, the littler chirpy birds, they really start diversifying in the cooler climates. Another interesting example of these birds occurs in the Pleistocene. These large flightless carnivorous terror birds, larger than a human. So again, sometimes it can be kind of hard to look at birds and be like, oh yeah, those are relatives of dinosaurs. If you saw one of these terror birds, you would not think that the case. These were definitely preying on our early ancestors, and they went extinct relatively recently, just tens of thousands of years ago. And so these things were truly formidable, and I'm frankly glad that they're gone. Mammals also expand into the skies. So birds are in the skies. Mammals think, hey, that looks fun too. The skies are open. The smaller body forms, mammals start exploding in this niche. The Chiroptera bats are the second most diverse animal order, second only to the rodents. And again, as we saw in some of the earlier exercises, mammals take a slightly different approach, where they use all 5 of their fingers to support their wing membrane, whereas pterosaurs only used the ring finger, and birds end up using feathers. And bats are very important pollinators, and they're also very important insectivores. And coolly, they use this echolocation where they send out chirps, and it kind of bounces off, and they kind of see with that echolocation. So mammals kind of took over the skies and share it with birds. Mammals also went back into the seas and share it with the fish. So all those marine reptiles, ichthyosaurs, plesiosaurs, mosasaurs, they're all extinct. Mammals seize this opportunity. Bony fish also expand into some of those roles. Sharks in particular, the cartilaginous fish, do pretty well also. We see here this kind of transition, just like we saw with Tiktaalik moving onto the land. We see sort of this reversal with mammals moving off of the land, and we see sort of the opposite trend, where we see initially something that sort of dabbles in being in the water, becomes kind of more and more adapted over time, where they probably have webbed feet and are competent swimmers, but they're still comfortable on land, to more and more developed to marine life, where dolphins and whales cannot function whatsoever outside of the water. What evidence do we have? Well, we see a lot of these transitional forms, which usually we don't see in the fossil record. So this is a very good example of kind of transitional forms. Very few missing links in this transition. We also see the vestigial rear limbs still present in whales and dolphins. They still have the remnants of their old pelvis and rear legs. And again, blue whale, the modern blue whale, is the largest animal to ever exist on the face of the earth. Even the biggest, whatever largest sauropod dinosaur it was, whether it be Argentinosaurus or Dreadnoughtus or Patagotitan, they all pale in comparison to the blue whale. We see the largest modern herbivore elephant. They're mammals as well, sort of, on the same sort of scale as dinosaurs, a little bit smaller. But mammals really start taking over and filling these niches. Getting into the actual true, what we call the Ice Age, the Pleistocene, the time where we're kind of bouncing back and forth between Ice Age and not Ice Age, mammals really adapt especially to these herbivorous roles. They've been doing so since the extinction of the dinosaurs. Just like we saw with the dinosaurs, there was this trend towards kind of increasing body size over time. There's more nutrients around, they're getting bigger, and they're exploiting these new deciduous forests, these new angiosperm forests. Most of the Pleistocene megafauna, these really truly large animals, you see here's a human for scale. We got mammoths, mastodons, the Irish elk, a very large camel, the giant sloth, short-faced bear, saber-toothed tiger, Gigantopithecus, all these very large mammal megafauna. Mostly they're herbivores, but some of them are predators. Again, we see that arms race between herbivores get larger and larger and larger. Carnivores get larger and larger and larger in response. And so these are the Pleistocene megafauna. Unfortunately, they're extinct. The biome that they lived in, the mammoth steppe, was during the last glacial maximum. It was the world's largest biome. So this is what that maybe is usually portrayed as. We usually see like a barren, snowy kind of ice scape. But really it was very productive. It was a very productive environment with lots of grass, lots of herbs, lots of shrubs. And you see that this environment kind of occupied the entire northern reaches of what's now Siberia and northern Europe. It's much more productive than the modern tundra is in those regions. One of the reasons is that the mammoths actually sculpted this environment. They kept vegetation down and they really created this environment for other organisms. They were a keystone species. In fact, there's been some efforts recently in Siberia to kind of rewild the Siberian tundra with large herbivores like bison and elk to try to kind of mimic the effect of the mammoths. And there's actually even been some very wild proposals. We do have mammoth DNA. We've been able to extract it from exceptional specimens. There's actually been a, de-extincting the mammoths and letting them repopulate this and reestablishing this mammoth steppe. That's kind of a genie that you can't put back into the bottle. It's fun to think about, but it's also pretty wild. The megafauna go extinct about 12,000 years ago, when, or at least very closely related to when humans arrive. You see humans arrive, and then there's a little bit of a lag, there's extinction, and then they're finally hunted out about 20,000 years ago. Some remnants held on till about 4,000 years ago. Maybe it was humans. So that's, we're kind of running low on time, so I apologize. I'm going to start going a little bit quick here. What is a human? So one of the key characteristics of the Cenozoic is the evolution of humans. We wouldn't be here if it wasn't for that. So hominins are defined by a few characteristics that separate us from the other humanoid apes. So one of the characteristics is bipedalism. We walk upright on two legs. Other apes can do that occasionally, but they are not adapted to do it. That allows us to put our big old brain right on top of our spinal column and allows it to increase in size and increase in complexity and increase in capability. And it gives us our reasoning skills that sort of separates us from the other animals, or at least we claim that it does. And the other thing that this allows us to do is because our brains being large, currently the size of our skull is limited by the size of the birth canal. And so humans are born relatively small with relatively small heads, and it takes an extended period of time where our noggins grow. And it takes a long period of time, longer gestation period, longer growth stage. That's an advantage for us eventually when we reach the fully developed brain stage. So what was the first hominin? If we look at the reconstruction here, Again, we often see that march of progress from like chimp to human. Again, that's totally wrong. Don't, there's a big red X on the last slide for a reason. You see that the tree of life is much more branching, and there's all these different hominin ancestors. So where do we draw the line and say that, aha, this is human? What is it that makes a human? We've seen this with the dinosaurs, where we have trouble assigning these basal transitional forms to the individual groups. We have the same problem here. How do we draw this bin? Where do we draw that line between what is human? This is a reconstruction of Australopithecus, and this is the fossil material from Lucy. I actually got the opportunity to see the fossils when they came through when I was in Houston. Very cool to be able to look upon, one of our earliest ancestors. Humans originated in Africa, again in the Rift Valleys, the Olduvai Gorge, started moving out about like 200-ish to 100,000-ish years. These dates are always in flux as we learn more about our ancestry. But we weren't the first hominids to leave Africa. So as we, modern Homo sapiens, were leaving Africa, we encountered Neanderthals in Europe, and we encountered Denisovans in Asia. They had left much earlier. And there's a big debate about what happened when we interacted with these. There was definitely interbreeding. So was it a peaceful, loving relationship? Or was it more warlike, which it would sort of be indicated by our interactions in the modern world? But humans at this time are also starting to become a little bit more home-centered. They have like a home base. And there's less hunter-gathering, and they're more efficient with their time. For the first time, we have free time. We don't have to struggle quite as much. And that gives us the luxury of making things really for beauty as opposed to function. So the earliest non-tool sculpture appears about 70,000 years ago. The earliest cave art appears about 40,000 years ago. And that's significant because we're using these symbols to communicate. And these symbols last a lot longer than we do. 40,000 years later, we can still see what these original artists were trying to communicate. We may not know exactly what they were trying to say, but we can still see it. For the first time, animals, us, are able to send messages through time. We're really transcending our own limited lifetimes. And then every generation is able to build on the knowledge of the first one before. It really enables the scientific process and all of the advancements that come with that. And eventually we get to the kind of the modern era. Eventually Homo sapiens outcompete all of the other hominins. Neanderthals are gone. Denisovans are gone. There's a big question kind of why. How did we win the evolutionary arms race? One initial idea was that we were smarter. Our brains were bigger and we were more capable. It turns out that Neanderthals actually had a larger brain case. The size of the brain and the complexity of the brain aren't always related. So we may in fact be smarter than Neanderthal, but if we were, it wasn't by a lot. Potentially we were more savage than Neanderthal, and we outcompeted them in that way. That would be a bit unfortunate, but potentially that was our main advantage. And it leads us to now where we're able to really kind of ponder, why are we here? And ultimately, where are we headed? We've taken this trip through geologic time and seen how life evolved on this planet. We're here in the present day, and in many ways, we're now in charge of where the Earth goes from here. We have such a large impact on this planet that we can control the future. It really is the Anthropocene, the age of man. It's come a long way from leaving muddy footprints in the Laetoli, in the Olduvai Gorge, to leaving dusty footprints on the moon. And hopefully we're able to continue in a positive path, and we don't destroy ourselves. And remember that you have a hand in that. You're the next generation of scientists, and I hope you're able to accomplish things that we were not able to. That's all I got for today. Hope you enjoyed that, and goodbye.